I want to spend a few minutes today talking about the speed of EMR. We know now that the speed of EMR in general, any kind of EMR in a vacuum is 3 times 10 to the 8 meters per second. But how do we know that? There's been probably hundreds of experiments done over the last several hundred years to try to determine the speed of light or the speed of EMR in a vacuum. Some of them have been pretty successful, some not so successful. I want to describe 2 of them today. One, very, very good, very successful and accurate. The other one, not so accurate, not so successful. And then we'll try to determine what the difference is, why one of them is more accurate than the other one. The first one that I want to talk about is one that was performed by Galileo. In this experiment, we have 2 hills, a kilometer apart from each other. Galileo has a light. We'll call it light number 1 on the first hill, but it's covered up. It's a lantern, it's a flame that's covered up with a sheet or something like that so that nobody can see it. There's another light on hill number 2 that's covered up by Galileo's assistant. So Galileo is over here on hill number 1 with light number 1, and his assistant is over here on hill number 2 with light number 2. Both of them have it covered up. Now Galileo uncovers his light, and as he does that, he starts his little stopwatch. And when I say that, I use that term loosely. Of course, he doesn't have a stopwatch. I don't know what he would have used to time this, but something, some time measuring device that he had, he starts it now. He uncovers his light, light number 1, and starts a stopwatch. Now, his assistant over here on hill number 2 doesn't see the light instantly, but does see it very, very soon, right? Very soon after Galileo uncovers it, the light makes it the kilometer distance, and his assistant sees it. When his assistant sees light number 1, he uncovers his light, or his lantern. So now both of them are exposed. Now, a small fraction of a second later, Galileo sees the light coming from hill number 2. So, hill number 1, Galileo uncovers the light, starts the stopwatch. The light travels over here towards hill number 2. Assistant uncovers his light when he sees it. The light from hill number 2 travels back here towards hill number 1. Galileo stops his stopwatch when he sees the light from hill number 2. Does that make sense? He knows the distance the light's traveled, right? The light has traveled from light number 1 to light number 2, and then back again. The light's traveled a distance of 2.0 kilometers. Galileo's measured the time here. He used a stopwatch or whatever device he had to measure the time that it took the light to travel 2 kilometers. He's got a time here. I don't know what that time would have been, but he's got a time. He does a little calculation. He measures the speed. Seems reasonable, right? But the results from this experiment are not even remotely close to being valid. Why not? What's the problem with this? Sorry? Yeah, human error is massive compared to the amount of time that it would take the light to travel 2 kilometers, right? Light travels at about 1 billion kilometers per hour. We know this now. He didn't at the time, but we know it now to be about 1 billion kilometers per hour, which is about 50 one-way trips across Canada. Canada is the 2nd biggest country in the world. Light could travel 50 times across the country in 1 second. That's how fast it travels. Imagine how fast it travels 2 kilometers. The amount of human reaction time in this experiment is massive compared to the amount of time that it would take the light to travel. Therefore, any result we get here, anything that we get, is not even remotely close to being valid. It just doesn't work. Even if you did happen to get a number that was close to the value that we know it to be, it would be pure coincidence. That make sense? All right. Here's another experiment. It was performed by a guy named Michelson that is much better. You'll see why in a few moments here. Michelson did an experiment where he had 2 hills as well, Mount Wilson and Mount San Antonio. These hills were about 35 kilometers apart. So instead of being 1 kilometer apart, it's 35 kilometers apart. Now, that's a lot more But still, reaction time would be really, really big compared to the amount of time that it would take for the light to travel that far, right? So although we're decreasing the effective human reaction time by quite a bit, still not nearly enough to make a huge difference. So there's something else that's going to happen in this experiment that's going to make this more accurate. It isn't increasing the distance. We do increase the distance, but that's not the important thing here. Here's what happens in this experiment. Two mountains, about 35 kilometers apart from one another. We've got a light on one of those mountains, Mount Wilson. That light we're going to turn on. It's going to release this little burst of light towards this octagon that we see right here. This is actually a rotating mirror. We can see that it has 8 sides to it. There's one flat mirror right here, one flat mirror right here, and so on and so on and so on. And it can rotate this way. Here's what we want to do now. We want to start this mirror rotating. We want to get it rotating at just the right speed, just the right frequency to observe what we want to observe. So here's how it goes. We start this light rotating, we turn the light on, and the little pulse of light goes toward the rotating mirror. Notice at this point, the little pulse of light reflects off of side 4 of the mirror. Got that? Reflects off of side 4. Now, if it reflects just right, then it will come down here as the mirror continues to rotate towards Mount San Antonio. Reflects off of Mount San Antonio and comes back and reflects off of side 5 of the mirror. Notice something really important though. During the time that it took the light to travel from this side to this side, side 4 has moved 1/8 of a rotation. Side 4 was right here, right? Now side 4 is right here. So during the time that it took the light to travel 35 kilometers here and another 35 kilometers here, during the time that it took the light to travel that distance, the mirror has made 1/8 of a rotation. Does that make sense? Side 4 that was right here, side 4 is now in exactly this position. In order for this little flash of light to reflect and get observed by this observer, by the person or the whatever detector you have over here trying to detect the light. If it didn't travel exactly 1/8 of a rotation, watch what happens here. Let's go back here. The light reflects off of side 4, comes down here, reflects off of Mount San Antonio, comes back here, starts reflecting. But watch if this mirror hadn't made exactly 1/8 of a rotation. Just a little bit less than 1/8 of a rotation. Now this light ends up reflecting up here somewhere. It never gets observed. If the EMR is getting observed, then the mirror must have made 1/8 of a rotation. Does that make sense? We know the frequency of this rotating mirror. Okay, whatever it is, we know the frequency. From the frequency of the rotating mirror, we can find the period, which is the time for one complete rotation. And from the period, divide it by 8 to find the time for 1/8 of a rotation. That's the time we want, because that's the time that it took the light to travel the 70-kilometer distance. So, we know the distance traveled. If we can calculate the time for 1/8 of a rotation, then we can calculate the speed of light here. Why is this better? Why does this give us a result that's way better than Galileo's experiment that was performed? Gave us the number that didn't make any sense. What makes this one better? We might be off. Listen, we might be off in our measurement of the frequency. Usually it's somewhere around 500, 600, 700 hertz. We might be off.
The measurement of time isn't just dependent on the
Yes. We might be off with our frequency, but how much are we going to be off? Like, let's say the frequency is 600 hertz, and we measure it to be 630 hertz. It's 5%. That's not anywhere close to as high as our reaction time, right? This is a mechanical device, and there's not certainty with a mechanical device, but there's a lot more certainty than there is with human reaction time. So we've eliminated human reaction time. Even though our distance is still pretty small, because we've eliminated human reaction time, it doesn't matter as much that our distance is small. Ideally, we use a bigger distance and eliminate human reaction time. But human reaction time is the biggest part of it. Yeah?
How do they know which number it is?
Exactly. That's a good question. The question was, how do we know which side of the mirror it hit? Like side 1, side 2, side 3, whatever. In the end, here, let's erase this. And let's go back here. So let's say in this case it hits side 4. Okay, that's an arbitrary number that I put beside side 4. Okay, it hits a side. Okay, and if it reflects off of this rotating mirror, comes down to Mount San Antonio, reflects back and gets observed, we know that it had to hit 2 sides perfectly, right? Now, which side did it hit? Was it side 4 and side 5? Was it side 4 and side 6? Whatever. Okay, forget about the numbers for a second. Okay, reflects off of a side right there. If this mirror is not rotating, okay, if this mirror is not rotating, it's going to reflect off of side 4, come back here, reflect off of side 6, get observed by the observer. But as soon as I start rotating it slowly, then all of a sudden the angles aren't going to be right. So it's not going to be observed. But if I increase the frequency a little bit more, a little bit more, a little bit more, as soon as the EMR starts getting observed by the observer, it must have made 1/8 of a rotation. Now, if I increase the frequency even more, then it could have made 2/8 of a rotation during that time. Increase even more, it could have made 3/8 of a rotation during that time, right? What I want to do is hit the first time that EMR is observed by the observer. And then, was it side 4 and side 5? I don't know. It was 1/8 of a rotation. Okay, I've just put numbers on there to kind of, so that you can see that it's made 1/8 of a rotation. So that you can see that during that time, what I have labeled as side 4, sorry, that was, I spun that one, right? It was supposed to be right there. What I had labeled as side 4 made exactly 1/8 of a rotation. Does that make sense?
Also, the
Yep.
Mount San Antonio, like, what do they do with the mirror? Like, how do they like the mirror?
That's a good question. Yeah, that's a good question. The mechanics of something like this, I can't tell you exactly how that would have been done. Generally, what we see is, in the description of this, is the mirror on Mount San Antonio is a curved mirror as opposed to a flat mirror. But still, the alignment of that would be tricky, right? I would suspect that it would have taken a lot of trial and error to make that work. Probably trial and error with the mirror not rotating first, because theoretically, if everything is aligned properly, it should work every single time until you start rotating the mirror, right? So I would imagine they probably would have, that Michelson would have probably aligned it with it turned off, and then started, once he had it aligned, turned up the frequency until he saw it again. Yep. I don't know, actually. It's a good question. I'm not sure.
You know, like the general time frame?
The time frame. I thought you said where.
Oh,
That's a good question. I want to say, that's a good question.